everyone, welcome back. I hope you all are fine, fit and healthy. Okay, so this is the fourth lecture for class 12 and we are doing solution chapter. So in this chapter we have covered a lot so far. The topics that we have covered is how to determine concentration of solutions. We have studied about types of solutions. We have studied about vapor pressure. We have studied about Henry's law, Raoult's law, okay, and azeotropes. And then yesterday we covered colligative properties. Colligative properties are those which depend on the number of solute particles and they do not depend on the nature of the particles. The first colligative property that we discussed yesterday was relative lowering of vapor pressure. We also derived the relation. If you remember, the relation was Pa naught minus Pa by Pa naught equals to chi B, where chi B is the mole fraction of the solute. So I had to conclude my class yesterday at that point due to time constraints. So numerical relating to this relative lowering of vapor pressure we'll do today in the first section. See, I've written the question on the board. Let's read it. The vapor pressure of pure benzene at certain temperature is 0.85 bar. As I read the question, I keep on writing the given. So let's write given. It's given vapor pressure of pure benzene. So definitely it becomes Pa naught is equal to 0.850 bar. A non-volatile, non-electrolyte solid. That means this is the solute. A non-volatile, non-electrolyte solid weighing 0.50 gram. That is Wp is equal to 0.50 gram. Is added to 39 gram of benzene. So that will be Wa, 39 grams. Molar mass of benzene is 78. This information is given in the question. So Ma is equal to 78 gram per mole. The vapor pressure of the solution then is 0.845 bar. Okay, that means after preparation of the solution, the vapor pressure of the solution goes to 0.845 bar. What is the molar mass of the solid substance? That means in your question they have asked you to find Mb. Okay? Now, so this is our formula. This is our formula. We'll use this formula to calculate Mb. Let's start. We'll start here only. So we have Pa naught minus Pa by Pa naught equals to chi B. Now this chi B we had seen yesterday, we can write it as Wb into Na divided by Mb into Wa. So let's put the values. This is 0.850 minus 0.845 divided by 0.850 equals to Wb is given as 0.5, Ma 78, Mb we don't know, and Wa given in the question is 39. Okay, if you solve this part, you are supposed to get 0.005 divided by 0.850 equals to, this will come up to let's leave it as such, 0.5 into 78 divided by Mb into 39. So let's take Mb this side. So Mb will be 0.5 into 78 into 0.850 divided by 0.005 into 39. Okay? If you solve this, you are supposed to get 170 gram per mole. This is the molar mass of the solute that will dissolve in 39 grams of benzene. This is how you're supposed to use the required information, put it in the formula and get your answer. Now, it is not always necessary that they will ask you to find ND. They might ask you to find the relative lowering of vapor pressure, any one of the factors that is present in the relation. Okay? So, numericals with this also, it will be there for you in the assignment. Clear? Alright. Next, let's go to the next colligative property. The next colligative property is, so we'll discuss the next colligative property now, that is elevation in boiling point. Elevation in boiling point. Now, before we start discussing about this colligative property, we have to first understand what is boiling point or what is boiling temperature. About boiling point or boiling temperature, I had discussed in my previous lecture also. But still, let me just give you the definition once again. Boiling point is the temperature at which the vapor pressure of the liquid, matches the atmospheric pressure. At which the vapor pressure of the liquid becomes equal to the atmospheric pressure. Now, if in that case we prepare a solution of non-volatile solute in a solvent, we found out that the vapor pressure of the solution decreases. If the vapor pressure decreases, technically it should take longer time for the solution to boil so that it matches with the atmospheric pressure. So if that happens, your solution will be boiling at a higher temperature compared to the solvent. Clear? That means solutions should have a higher boiling point compared to the solvent. Let us find this out graphically. Okay? Okay. So we'll plot the graph by taking vapor pressure along this axis and temperature in Kelvin along this axis. Now we are saying that boiling point is the temperature at which the vapor pressure of the liquid becomes equal to the atmospheric pressure. Now how much is the atmospheric pressure? Atmospheric pressure is 1 atm. That is the standard pressure. So I'll choose this point to be the atmospheric pressure. Okay, now we will draw two curves. Curve A and B will be for the solvent and C, D will be for the solution. Okay, C and D will be for the solution. Now, you see here the solvent, the curve for solvent matches that of the atmospheric pressure at this point. So let us draw this. And it will start boiling at this temperature. So I'll take this as TB naught. Alright? And that for solution matches the atmospheric pressure at this point. So this will be TB. Okay? Now, the difference in boiling point, that is delta TB, will be TB minus TB naught. So this will give me the elevation in boiling point of the solution that is taking place due to addition of the non-volatile solute. So delta TB is known as elevation in boiling point or boiling point elevation. So boiling point elevation. Clear? So we have found out that from the figure that solution boils at a higher temperature. Now, it has been experimentally found out that delta TB is directly proportional to the molar concentration, MOLAL, molar concentration of the solution. Okay, the proportionality sign is replaced by a constant Kb. What is Kb? Kb is the molar boiling point elevation constant, which is also known as ebullioscopic. Ebullioscopic constant. Let me just check the spelling. Ebullioscopic constant. Okay. So Kb is the molar boiling point elevation constant, which is also known as ebullioscopic constant. Clear? Let's elaborate now. I'm rubbing on this part. So this diagram also should be there when you prepare your notes. Okay. Now, so we are having delta Tb is equal to Kb into m, where m is the molality or molar concentration of the solution. If the molar concentration of the solution is 1, then delta Tb becomes equals to Kb. So how can we define Kb? Kb is defined as the elevation in boiling point for a solution which contains 1 molar solute or 1 gram mole of solute. Okay, so this you must remember. Done? Now, with this relation, that is the relation for the colligative property of elevation in boiling point, we will derive the relation for Mb, that is molar mass. So let's start. Determination of molar mass of solute. Determination of molar mass of solute. Okay, we know that delta Tb is equal to Kb into m. Okay, now m is molality. The definition of molality is moles of solute by mass of solvent in grams. If I write, I have to divide, so that goes up, that will become into 1000. Now, molality is number of moles. Now, number of moles is given by given mass. This is what we have been choosing as our symbol, as our representation from before. So, given mass by molar mass. Now, mass of solvent will be Wa. Okay, so let's put this information here. So we have delta Tb is equal to Kb into Wb divided by Mb into Wa into 1000. This is the relationship. Let's take Mb this side. So Mb will become Kb into Wb into 1000 divided by delta Tb into Wa. This is the relationship for molar mass of solute for the second colligative property, that is elevation and boiling point. Now there is one information that I want to give you here. You must remember that the molar mass of the solute is inversely proportional to the colligative property. This you need to remember because when we go ahead in the chapter and we discuss about abnormal molar mass, this information is very much necessary. So molar mass and colligative property are inversely proportional. Okay? So this is about elevation and boiling point. Let's try to do a numerical then. Alright, so we have just finished discussing about the second colligative property, that is elevation and boiling point. And what is the relation? The relation is delta Pb is equal to Kb into m. Now, there is one information that I want to give you here. Kb, that is the ebullioscopic constant or the molar boiling point elevation constant. Unit, how can you find out? So, Kb becomes delta Tb by m. The unit of temperature is Kelvin. and molality is mole per kg. So kV has units of Kelvin, kg per mole. Alright, so this is the information that you need to remember. Okay, so keeping this in mind, let's try to solve the numerical which I have written on the board. Let's read the question. Molal elevation constant for benzene is 2.52 Kelvin kg per mole. Molal elevation constant. So let me write it down. That is Kb is equal to 2.52 Kelvin kg per mole. A solution of some organic substance in benzene boils at 0.126 degree higher. That means this is delta Tb that is given to you. So delta Tb is equal to 0.126 degree Celsius. Higher than benzene. What is the molality of the solution? This is a direct question. We can put the values directly in the formula and get the answer. Okay? So we know that delta Tb is equal to Kb into m. We have been asked to find the molality. So molality becomes delta Tb by Kb. This is equal to 2.52 by 0.126. If you solve this, you are supposed to get 0.05 molar. That is mole per kg. Alright? Okay, so with this, we will stop our discussion about the second colligative property. We have, this is not the only kind of numerical. There will be numericals related to molar mass determination also. So that I have given in the assignment. Please try solving that, okay? Alright, so the next colligative property is depression in, okay. So the next colligative property is depression in freezing point. Now before you try to understand what is depression and freezing point as a colligative property, we must recall our idea about freezing point. Okay? In your junior classes, you have learned that freezing point is the temperature at which I am using the example of water and so ice and water. That means the solid and the liquid are at equilibrium. Yes, that is when your water will start to freeze. This condition can be achieved only when the vapor pressure of your solid solvent and the vapor pressure of the liquid are same. This can happen only when these two have the same vapor pressure, in simple terms. That means freezing point or freezing temperature is the temperature at which vapor pressure of the solid state of the substance and liquid state of the substance is same. Okay? Now, when we discussed about solutions of non-volatile solute in liquid, we found out that there is a decrease in vapor pressure for solutions containing non-volatile solute. If there is a decrease in vapor pressure, how is the freezing point affected? Okay, let us understand that graphically. Okay, so I'll take vapor pressure along this axis, vapor pressure along this axis, and temperature in Kelvin along this axis. Let's take, I'll use another marker. Let's take the curve AB to be for the frozen solvent. That means the example that we had chosen was ice. Alright? Now, we know that the vapor pressure of liquid solvent is higher than our solution. Let this be the curve of the liquid solvent. The liquid solvent. Okay? Now, the liquid solvent curve meets that of the frozen solvent at point B. Let this be BC. Okay? C. Now, we know that the vapor pressure of the solution is lower than that of the frozen solvent. The vapor pressure of the solution is lower than that of the liquid solvent. So, I'm putting this here. So, this is for the liquid solvent, this is for the solution. Okay? Now, let this be dE. Let this be dE. Now, from the plot, we can understand that this is the temperature at which our liquid freezes. So, this is the pure solvent, so I'll take it as Tf naught. And this is for the solution, so this will be Tf. The difference, delta Tf, is the freezing point, depression. Okay, now how is delta Tf, the colligative property, related to solutions containing non-volatile solute? So this figure that I have drawn is also important. Okay, let's continue from there. So we found that delta Tf is the freezing point depression, and it has been experimentally found out that just like elevation in boiling point, delta Tf is also directly proportional to the molar concentration of the solution. Okay, so delta Tf, we will replace this proportionality sign now with a constant Kf. So Kfm. What is Kf? Kf is the molar freezing point depression constant. Molar freezing point depression constant, or it is also known as molar cryoscopic constant. Alright, molar cryoscopic constant. Yeah? Now, just like we have done for elevation and boiling point, if the molality of the solution is 1, delta Tf becomes equal to Kf. That means the molar freezing point depression constant is equal to the depression in freezing point for 1 molar solution. That means if your solution has 1 gram mole of solute in 1000 gram of solvent. Clear? So this is very much similar to elevation and boiling point. Now let us do it for molar mass also. So molar mass determination. I'll rub the board. Molar mass determination. Molar mass determination. Okay. So we had del Tf is equal to Kfm. We know that molality is number of moles by mass of solvent in kg. Okay, if we take it in gram, we multiply 1000 here. Number of moles, we know that it is given mass by molar mass, and mass of solvent will be Wa. So if we put this here, we will have delta Tf is equal to Kf into Wb. If it is in gram, we need to multiply 1000 divided by Mb into Wa. Alright, so let's take Mb this side. Mb is equal to Kf into Wb into 1000 divided by delta Tf into Wa. This is the relation for the third colligative property, that is depression in freezing point. Okay, now with this relation, we'll try to solve a numerical. Alright, so let's try to solve the numerical for freezing point depression. Okay, I've written the question on the board. Addition of 0.643 gram of a compound to 50 ml of benzene. The density of benzene is given to you. Lowers the freezing point from 5.51 degrees Celsius to 5.03 degrees Celsius. If Kf for benzene is 5.12 Kelvin kg per mole, calculate the molar mass of the compound. It is very much understood that if you read the question, they have asked you MB. Okay? Now, let us write the information given in the question. Addition of 0.643 grams, so that is WB is equal to 0.643 grams of a compound to 50 ml. Now, volume is given 50 ml. Benzene density is also given. So, density is 0.879. Lowers the freezing point from 5.51 to 5.03. So, what I'll do, I'll directly take out delta TF, that will be 5.51 minus 5.03. This comes to 0.48 degrees Celsius. Okay? Now, we know that in our formula for molar mass, there is no space for volume. We need to convert this into mass, that is mass of the solvent. So, mass will be volume into density, that is 50 into 0.879. This will come to 43.95 grams. Okay. Now we have got all our required information. Kf is also given in the question, that is 5.12 Kelvin Kg per mole. Let's put it in the formula now. We know that Mb is equal to Kf into WB into 1000 divided by delta Tf into WA. This is equal to 5.12. WB is 43.95 into 1000 divided by delta Tf is 0.48 and WA is delta Tf is 0.48. I have put the wrong value. WB is 0.643. WB is 0.643 and WA is 43.95. Okay, so on solving this, you are supposed to get 156.06 gram per mole. That will be your molar mass of the compound. Alright? Okay. Okay, let's discuss about the last colligative property, that is osmotic pressure. Now, all of you are familiar with the term osmosis. What is osmosis? Osmosis is, a phenomena in which there is a flow of solvent molecules from a region of low concentration of solute to a region of high concentration of solute. Right? That means there will be a flow through, and the most important thing is you need a semi-permeable membrane. All of you know what are the semi-permeable membranes that we use, like parchment paper, animal blubber, so on and so forth. Okay? So, osmosis phenomena is very well known to you. Now, coming from osmosis, the colligative property is osmotic pressure. Now, what is osmotic pressure? I have made a figure on the board. I have taken two vessels. In this side, in vessel 1, I have only solvent, and in vessel 2, I have taken solution. Okay, both these vessels are fitted with watertight and frictionless pistons, and there is a certain pressure which is acting on these pistons. It is very well understood that these two are separated by a semi-permeable membrane, and there will be a flow of solvent molecules from this region to this region, and this will continue until both the solutions have the same concentration. Since they are flowing, since solvent molecules is flowing from this vessel to this vessel, this piston will tend to rise. There will be a rise in level in this container. If you want to stop osmosis, you will have to apply some amount of extra pressure on this side. You have to apply some amount of extra pressure on this side so that you can stop the flow of solvent molecules from this side, from the solvent side. This extra pressure that you supply is known as the osmotic pressure. So, Osmotic pressure will have to be applied on this side. The symbol for osmotic pressure is pi. Clear? So osmotic pressure is the extra pressure which has to be applied on the solution side to stop the flow of solvent molecules through the semi-permeable membrane. Done? Now, how do we relate osmotic pressure to colligative property? Let's see. It was Van 't who found that osmotic pressure pi is given by the relation CRT for dilute solutions. Okay? He found that the osmotic pressure is equal to the concentration of the solution, the molar concentration of the solution. That means C is the molar concentration here, molar concentration of solution. R, all of you know, is the gas constant, and T is the temperature. Okay? So, pi is equal to CRT. C is the molar concentration, R is the gas constant, and T is the temperature. Since this is a constant at a particular temperature, T will also be constant. So, pi directly becomes equal to C. That means, since osmotic pressure is directly proportional to the concentration of solutes, it becomes a colligative property. Is that okay? So, this is how we have related osmotic pressure to concentration of solute. Now, we will expand this relation. So, we had pi is equal to CRT. Now, C is a concentration, that means molar concentration, and molarity is number of moles of solute by volume of solution in liters. So, we can write this here. So, it becomes pi is equal to N by V RT. So, we can write pi V is equal to nRT. This is the Van 't relationship for dilute solutions for osmotic pressure. Okay? So, you must remember this relation. It is there for numericals. Using this relationship, we will again derive the relationship for molar mass of solute. So, molar mass of solute. Okay. We know that number of moles is equal to given mass by molar mass. So, let's put this here. So, pi V is equal to WB MB RT we had here. So, pi is equal to, just simply take MB directly this side. So, MB is equal to WB RT by pi V. This is the relationship for determination of molar mass from osmotic pressure. Okay? So, this much we will conclude today. Numericals from this section, discussion about types of solutions under osmosis, that is hypertonic, isotonic, reverse osmosis, abnormal molar mass, we will discuss in the last lecture. So with this, I'll conclude, and numericals, I'll give you the assignment. So kindly solve them and send them to the respective teachers. The email IDs to whom you should be forwarding your task will be mentioned at the bottom of your assignment sheet. Okay? Thank you everyone.